All right, so I'm going to tell you about some relations between the nearby Lagrangian conjecture and the algebraic K-theory of spaces. Um, so the story is roughly as follows. So about a year and a half, no, a little bit less, I was visiting Paris, and Sylvain gave this beautiful talk at Jussieu about this existence theorem for generating functions. And I just spent the last year of grad school trying to understand Waldhausen's algebraic K-theory from a manifold approach, this paper in which he tries to understand algebraic K-theory using smooth manifolds. And it was very exciting. And so I was talking with him over the past year or so, and then now we kind of realized that Mohammed and Thomas were thinking in very much the same terms. So these whole three sections, I think, are things that at the very least we all know. So I'm just going to say that it's joint. With Mohammed, Sylvain, and Thomas. And then I'm not sure if I will be able to get to this, but independently, I was thinking with Igusa in terms of the higher torsion of Legendrians, and well, it turns out that this also makes sense. Excuse me? What's that? Oh, this also makes sense for nearby Lagrangians, and okay, so it's still very speculative. So if I don't have time to get to it, then that's okay. But that's my plan for today. So the main protagonists will be tubes, and this is what a tube looks like. And so my main goal will be to explain the roles of tubes. But before I do that, let me try and whet your appetite a little bit by explaining at least some consequences that we can deduce with regards to the nearby Lagrangian conjecture. And so at the risk of boring experts, let me very quickly remind you of the setup of the nearby Lagrangian conjecture. So we have L and M closed, connected, and smooth manifolds. And so what's the definition? So a nearby Lagrangian is an exact Lagrangian embedding of L into the cotangent bundle of M. Okay, and so conjecturally, all are Hamiltonian isotopic to the zero section. But this conjecture, I think it's kind of not clear whether we should believe it or not, and indeed the jury is out. It is maybe hoped that the cotangent bundle of a smooth manifold, the symplectic geometry of the cotangent bundle of the smooth manifold, remembers some or all of the smooth topology of the base. But I think with respect to Hamiltonian isotopy classes, the main reason to believe this conjecture is that we can't find counterexamples. But maybe we didn't try hard enough. It is only known. Well, in the case of S1, I'm just going to say this is folklore, but here and anywhere else, if I have attributions wrong, then by all means, please correct me in the chat. For S2, well, in the relative case in which it only intersects, in which it intersects one fiber and only one point, I think this was shown by Eliasberg and Poltrovich. And in the general case, behind, and then we have S1 times S1. So this is Dimitri Blue. Okay, so it's not an overwhelming amount of evidence. So Yep, that's, for instance, for higher genus surfaces, we don't know whether it's true. Okay, so what? So in general, one thing that we do know is that the restriction of the cotangent bundle projection to L is a simple homotopy equivalence. Okay, so that means that it induces an isomorphism on the homotopy groups, and moreover, the simple, the fact that it's a simple homotopy equivalence has to do with pi1, but since today I'm going to be talking mostly about spheres, I won't dwell on this too much. But okay, so this is due to many papers by many people involving many different new ideas. So let me just very quickly review my understanding of how this came about. And again, you can correct me if I'm wrong. So homologically in the Maslov zero case, I think this was proved by Fukaya, Seidel, and Smith. Still in Maslov zero, but upgraded to a homotopy equivalence. This was Mohammed. Then together with Kragh, it was shown that actually the first Maslov class is always zero. So this is always a homotopy equivalence. And then moreover, they also proved that it's a simple homotopy equivalence. And I should all say these are all results using pseudo-holomorphic curves. But if you want to use finite dimensional methods for whatever reason, then there's also approaches using microlocal sheaves by Nadler and Guillermou. Okay.
Danny, there's a question from Igor.
So let's see. Can I even see the question? So I'm somehow not able to see the question. Could you read it?
Yes, I think it was a question about the cases in which the nearby Lagrangian conjecture are known. Igor, you're welcome to unmute yourself. The question was asking, is RP2 also known?
Not to my knowledge, but I could be wrong. Someone can correct me if I'm wrong.
I recall maybe high-end also being the case of RP2, but I might be mistaken.
Maybe RP2. Okay. Thank you, Igor. Okay, so let's go on. So in particular, something that is open is every Lagrangian L diffeomorphic to the base? This is completely open. So let's take something a little bit simple. Let's take just a standard sphere. So what is known? Okay, so here L is a Lagrangian homotopy sphere. So, okay, what can we say in this case? So let theta n be the group of homotopy spheres. So this is the group of homotopy spheres up to H cobordism with the operation of connect sum. Okay, this is a group. And then you have a subgroup consisting of those which bound a parallelizable manifold. Okay, so something that it's known is that the class of L is trivial in the quotient theta n mod bpm plus 1 when, so for n, let's see, congruent to 3 mod 4, this was shown again by Mohammed, and then the methods that he used were extended for n congruent to 1 mod 4 in work of Igusa and Smith, and then Kragh and Smith. Let me just put the three of them together. So when n is odd we know that every Lagrangian homotopy sphere in the cotangent bundle of the standard sphere bounds a parallelizable manifold. And today I'm going to give a constraint on the class of such L in theta n mod bpn plus 1 using only finite dimensional methods. And in fact, the logic of the proof can be arranged so that you're never using pseudo-holomorphic curves at all. And the results will be new for n even, where I believe nothing is known. Now, you might, of course, there's no particular value in not using pseudo-holomorphic curves. I just want to mention that because somehow everything that came before this can be done, say, using microlocal sheaves. However, the method that Mohammed used was constructing a high-dimensional moduli space of J-holomorphic disks. And so for those manifolds, at least with sheaves over Z, say, there's no possibility of getting to them. Maybe, as we'll hear later on in the seminar, if you do microlocal sheaves over the sphere spectrum, you have a possibility of getting here. But so far, pseudo-holomorphic curves were the only way, and now at least we can say something using the theory of generating functions.
Danny, there's a comment from Octav. Octav, you're welcome to unmute yourself.
It was just a comment. It's not even a question. So I was just saying that one can also view as open question whether exact Lagrangian in the cotangent bundle is exact cobordant to the zero section, because there is also a conjecture that exact cobordism is in fact Lagrangian isotopy, and so there is this implication too.
And embedded Lagrangian cobordant, yeah?
Yeah, correct. And so the idea to approach that would be to start with an immersed Lagrangian cobordism and try to see whether one can eliminate the singularity somehow.
Mm-hmm. Well, that's interesting. I mean, I don't know how much I will talk about this today, but the methods that we will show actually produced immersed Lagrangian cobordisms, and in fact, in some sense, they're unobstructed. So maybe there is some.
So this is not very surprising because of the categorical results of Foucault, Seidel-Smith, and Mohammed, and all these parts. So now we know that from these categorical results, you can deduce some geometry. But the difficulty is to simplify the geometry somehow. You know, it's like the H-cobordism theorem. The hard part was moving from cobordism with many critical points to cobordism with fewer critical points. And it's a little bit like that in this case too. But I don't want to interrupt, actually. I'm interrupted too much already.
No. That was a good comment. Thank you. So okay, so now let me tell you what we can prove. So it's not much, but it's something. So I need to remind you of what Kragh and Milner did. So what did Kragh and Milner do? So they showed that if sigma is a homotopy sphere, so, well, first of all, recall, sorry, this is wrong order. So let sigma be a homotopy sphere. So recall the Pontryagin-Thom isomorphism between the stable nth homotopy groups of spheres and the cobordism, frame bordism group of n-dimensional manifolds. Okay, so there is a map. There is a group homomorphism from theta n to the co-kernel of the J homomorphism, where the J homomorphism is a map from the nth homotopy group of the stable orthogonal group to the n stem. And I will describe the J homomorphism geometrically later on in the talk because it will be relevant. But let me just tell you what this map is. So the point is that actually, if I consider sigma, so they first of all, they proved that sigma is stably parallelizable. And then they proved that if you take the collection of frame bordism classes for all possible framings, then this is a coset of the image of J. Okay, and therefore you get that map just by sending sigma to the collection of frame bordism classes. And moreover, the kernel of this map is precisely the subgroup theta n BPN. And so hence, what do we see? We see that theta n modulo BPN plus 1 embeds as a subgroup of the co-kernel of the J homomorphism, okay? And in fact, it's always either the whole thing or it's an index 2, but I won't need that. I just will need to know that it's a subgroup of the co-kernel of J. Okay. So that's how the story goes. And I need one more fact. I need also to recall that if I take the direct sum of all of these homotopy groups, this is a ring. Okay, this is a ring, and I will be interested in the multiplicative structure. In particular, I'm interested in multiplication by this element eta, which is the Hopf vibration. Okay, so the Hopf vibration is an element S3 to S2. Pi ns is, of course, the limit in K of pi n plus K sk. And so in particular, the Hopf vibration gives me some element in the one stem. Okay. So then what? So let Hn be the image of the following composition. So I start with pi n minus 1. I multiply by eta. Okay, and then I just take the quotient map. Okay. All right, I can state now our main result. So theorem. So let sigma 0, sigma 1 be homotopy spheres. If sigma 0 admits a Lagrangian embedding into the cotangent bundle of sigma 1, then the difference between sigma 0 and sigma 1 is in the subgroup Hn. As above. Okay, so that's the statement of the theorem, and now I will explain some consequences that are concrete, and after that I will try to explain the full proof of this theorem. So, any questions about the statement? No questions?
Looks like there are no questions. Looks like there are no questions currently.
Okay, so let's see some corollaries. If I have a Lagrangian homotopy sphere in the cotangent bundle of the standard sphere, then the connect sum available itself bounds a parallelizable map. Okay. Proof, eta is 2 torsion. End of the proof. Okay. And so what? Well, let's see some examples. So when n is equal to 10, let me see. When n is equal to 10, this group has size 6, and there's only one possibility left, only one exotic possibility. Is not ruled out. And as another example, if n is equal to 18, then this thing has size 16, and only 3 possibilities in this case are not ruled out. So this definitely has some non-trivial consequences, but at the same time, it's clearly not as powerful as you would like. But okay, it is what it is. So let me also note that if L is like this and n is even, then the connect sum of L with itself is actually diffeomorphic to Sn. And this is just because, in this case, Bpn plus 1 is equal to 0. So actually for n even, the conclusion is much stronger because you don't have things like the exotic 7 spheres, which are, the classification is much subtle. It has to do with surgery theory. In this dimension, there is no surgery theory, so you get a stronger conclusion. More, so suppose that you're so lucky, that the dimension that you're in happens to multiply all of pi n minus 1 stable into the image of Jn. Then any Lagrangian homotopy sphere L is 0 in theta n mod Bpn plus 1. N even and not equal to 4. Sorry, so I'm using the H cobordism theorem there to conclude that theta n is the same as the set of as exotic smooth structures. But for that, I need the essential assumption that n is equal to 4 because the H cobordism theorem is not true for n equals 4. And so let me just jumble these two together. And so n equal to 4 even, here it actually implies that L is diffeomorphic to Sn itself. Okay, and so you might say, well, okay, that's kind of a strange condition. How on earth am I going to check whether that condition is true? And indeed, for any given n, verifying whether that condition is true is a non-trivial problem in stable homotopy theory. However, eta is 2 torsion, and there are some existing computations for the 2 primary part of the stable homotopy groups of spheres. And so, for example, we can just look at known computations in the literature and conclude that, well, this group isn't 0, so the conclusion is not trivial, and the assumption of the theorem is satisfied. For example, when n is equal to 8, 10, 14, 16, 19, some other n's. Okay, and so in particular, we see that for n equals 10, the case we saw before, the last possibility is rule out. And in fact, for n equals 18, only one possibility remains, because you can check if you look at the tables that in this case, this is just a single coset. However, I do not know how to exclude this possibility. So combining this with literature, n equals 18 is the smallest dimension. In which we do not know that L is 0 in theta n mod Bpn plus 1. Okay, so those are some of the first consequences that we're able to reap from the algebraic K-theory of spaces, and I'm optimistic that we'll be able to extract more, but at least this is something concrete that I can give you. And now for the rest of the talk, I want to explain where this comes from. So I'll stop with the questions.
I put a question in chat, which isn't really a question about the math, but did you ask the computational homotopy theorists what they know about this action of eta? I mean, of course, the literature says this, but they've been doing a lot of computations recently using homotopic methods. And I wonder what, if any of them have any consequence for this problem.
I mean, I asked a couple of homotopy theorists, but neither of them were actively doing research in this. So As far as
Okay.
they knew, there's nothing obvious known about this, but it's possible, like you say, that some recent developments have nothing to say.
Okay, thanks.
Everyone seemed to tell me, yeah, that it's a hard question, understanding the multiplicative structure.
Great.
But yeah, I don't have anything else to say about it at this point.
So Danny, can I also ask a question? So
Yeah.
can you just say what you get in n equals 10 case for those of us who don't really understand what's going on?
Oh, in n equals 10, it's just, I mean, I also don't understand what's going on, but I can check at the tables of atom spectral sequence, and you see that this condition is confirmed. So in n equals 10, every Lagrangian homotopy sphere bounds a parallelizable manifold.
And you wrote something about in the page before. Can you scroll up a little bit?
Well, interesting. So I'm trying to scroll, but I think I somehow lost control.
I see. So that's an impossible. Okay.
So
Maybe
let me
my
just,
question ends here.
I need to stop sharing and do this again, apparently. So let me just do that. So here?
Yeah, so you wrote that and when n is not equal to 4, and even then L is diffeomorphic to Sn.
Yeah, so for n equals 10, I can guarantee you that any Lagrangian homotopy sphere is diffeomorphic to the standard 10 sphere.
Okay. Yeah, that's what I thought, but since you didn't say it, I thought maybe I was missing something. Okay.
Yep, that is correct. So for all of these dimensions that I've listed down here, we know that any Lagrangian homotopy sphere is diffeomorphic to the standard sphere. Okay, any more questions? Okay, so now we're going to start talking about our main protagonist, the space of tubes. Okay, so let EK in Rn be a vector space. Okay, and so I'm going to define the rigid tube TE. And so this is a codimension 0 submanifold with boundary. And it's the following thing. So E is some k-dimensional linear subspace of some Rn. Okay, and now this Rn, you put it inside. Let me use a different n, because otherwise this is going to be very dramatic. Capital N. Okay, like this. Yeah. So then you put one more direction like that. Okay, and then you take the unit sphere of E. And along that unit sphere, you're going to do a standard handle attachment to this whole area down here, xn+1 smaller or equal than 0. So to that, you do the standard handle attachment, and that gives you some codimension 0 submanifold of Rn+1, which is everything that is below this rigid tube, and that's the rigid tube. So it includes all this area inside the tube and everything that's down here below. Okay, so that's a rigid tube. And then what's a flabby tube, or amongst friends just a tube? So let's call it Kn tube, is the image of T under a compactly supported isotopy of Rn+1. So what is a flabby tube? Well, it might look something like this. Okay, so this is a flabby tube, and it's standard at infinity because it's just the image under a compactly supported isotopy. Okay, any questions about the nature of tubes? Okay, so now definition. So a tube bundle is a fiber bundle of manifolds with fibrous tubes, but I want all the tubes to be contained in a fixed Rn plus 1. Okay, so it's a fiber bundle of manifolds, but it's not just that the fibers are diffeomorphic to tubes, they are really codimension 0 subsets of Euclidean space. Okay, and on such a bundle, I will consider functions which have the following properties. So the boundary of every tube, well, this is the restriction for every fiber. So this is a regular level set. And 2, your standard outside a compact subset. Okay, so there's a canonical function like this on any rigid tube. So let me just draw it for you, and it's the one that you think that only has one critical point, and this is the critical level set, and then all the other level sets are regular. So this is the level sets in one direction. These are the level sets. Okay. So in this example, the function only has one critical point, but in families, the tubes might be very complicated and there might be many critical points that move around. And then I just want an extra condition of regularity. I want that the fiber-wise derivative of the function is transverse to 0. Okay. So these are the functions on two bundles that I will be considering. And then what is the surf diagram? The surf diagram is defined to be the set of pairs M comma Z, such that Z is a critical value of Fm. So this is the surf diagram. Okay. So you know, maybe I have a tube bundle like this, and maybe it's moving around or something. And so as you try and put a function on it, you'll find that some critical points have to be born or die, and so you get a surf diagram. And so sorry, and I apologize to the experts. I'm about to finish, but I just wanted to define what generating functions are from scratch. So let me just tell you what the front projection is. The front projection is the map from the 1 jet space to the 0 jet space that forgets order 1 information. And well, the 1 jet space is just the cotangent bundle times R. And so this projection is thus just the cotangent bundle projection times the identity on the R factor. We call it pi front. So this is the front projection. And finally, definition. I say that a Legendrian is generated by a function f as above if the surf diagram of f is the front projection of lambda. Okay, so that's what it means by Legendrians to be generated. And I will say that an exact Lagrangian is generated by a function if its Legendrian lift, or one of its Legendrian lifts, doesn't matter, is generated by a function in this sense. Okay, so that's the definition of two bundles and the functions that we're going to use on them. Any questions about that? Okay, so let me give an example. If I have a bundle of rigid tubes, where E is a vector bundle, then there exists an F sub E with one critical point per fiber. So what you should think is that F sub E is essentially a family of quadratic forms whose negative eigenspace is given by E. So maybe this is your vector bundle, and here we have the family of corresponding rigid tubes that, like I say, you obtain these by attaching on the unit sphere. And then you can clearly see that there's just the standard function. I can rotate it around and it would give me a surf diagram that's just a copy of the zero section. And so on any rigid tube bundle, I can generate the zero section, and that will be important later. Okay, so great. So now let me say that if you believe the nearby Lagrangian conjecture, and you combine this with the homotopy lifting property, for generating functions, what this implies, by what I just said, is that every nearby Lagrangian admits a generating function on, well, in fact, any rigid tube bundle. In particular on the trivial bundle. Okay, so the nearby Lagrangian conjecture predicts existence of generating functions on tube bundles. This is wide open. Even having this would not necessarily imply all that much as far as I can tell. But in any case, this is something that I don't know whether it's true. However, there is the following recent progress in this direction.
Sorry, Danny.
Yeah.
Don't you need to stabilize?
Yes.
Okay, but the way you wrote it, people might be confused and thinking that you can keep the dimension fixed.
Well, there's no dimension here.
But when you write it admits a generating function on any rigid tube bundle.
Oh, thank you.
Depends what you mean.
Yeah, thank you. Indeed. Okay, so I wanted to brush this under the rug because I'm going to talk about stabilization later, but indeed I can't really do it unless I cheat. So there is indeed a stabilization procedure on tube, which plays well with the notion of stabilization for generating functions, and so this is all hidden in this after stabilizing, and I will explain this a little bit better in just a moment. Okay, thank you. So. However, you have the recent result in this direction by Abouzaid, Courte, Guillermou and Kragh. And their theorem says the following, that any Lagrangian homotopy sphere admits a generating function on some tube bundle. Okay, and in the general case, when the base is not Sn, they prove that every nearby Lagrangian admits a so-called twisted generating function. But I want to keep this talk as simple as I possibly can. And so let me not talk about twisted generating functions and just concentrate on the case of spheres where, like we saw, we can already reap some applications. But now we're all talking together, and we think that some of what I'm explaining today might extend over to more general basis. But yeah, let me not say anything more about this. And I also will say that once you have the existence of some tube bundle, then suddenly you can start now bringing invariants from tube bundles to define invariants of Legendrians. And this is the subject of my present work in progress with Kiyoshi, trying to use the higher Whitehead torsion of tube bundles to define invariants of nearby Lagrangians. And yeah, so that's something that is possible. I mean, you can always do it, but the theory has a chance of being non-trivial now that we have this theorem. So, oh, and one more thing that I will say is that from now on, all that I will prove are theorems about Legendrians which admit generating functions on tube bundles. Okay, so much more general than nearby Lagrangians, no doubt. And we're using this theorem to just prove existence of a generating family. But what I've explained applies more generally. However, if you want to touch the group BPN plus 1 of those which bound parallelizable manifolds, then you're going to have to use the condition that the Lagrangian is embedded more powerfully than just using it to establish existence of a generating function. Okay, so now let me talk about how this relates to frame bordism classes. So let W to Sn be a tube bundle. So consider a fiber-wise vector field such that the restriction to every fiber satisfies the formal conditions equivalent or corresponding to the ones I put for generating functions. So I want this to be outwards pointing along the boundary of the tube. And I want this to be standard outside a compact set. And I want 0 to be a regular value. Okay, so then an easy lemma is that the class of the inverse image of 0 framed by the differential. Let me just write it like this. So the differential gives you a framing. This is independent of X. And the proof is to perturb a convex interpolation. Okay, so you can perturb a convex interpolation between any two X's in this definition, and that will give you a frame bordism between them. So then it doesn't matter which vector field I use to define this frame bordism class. And therefore, I get a well-defined class just in terms of the tube bundle. Okay? It's called the frame bordism class of the tube bundle. Okay? And so an easy lemma is that if I have a Legendrian which is generated by a function on a tube bundle, then the Legendrian framed with the canonical framing coming from the generating function, well, this is just the frame bordism class of the tube bundle. Okay, in proof, this is just that by definition, the framings are the same. So this is just tautological. And therefore, if I want to understand the frame bordism classes of nearby Lagrangian spheres, because by this theorem they always admit generating functions, I am led to consider two bundles and their frame bordism class. And that's where algebraic K-theory comes in. Okay, so I'm on section 3, and now I will explain the Waldhausen derivative. So let Tkn be the space Kn tubes. So there are stabilization operations, as Mohammed was pointing out, and there's two of them. One is very stupid. You just take a tube and you include it in a higher codimensional linear subspace. So you just add this direction, but the sphere, the attaching sphere, basically stays the same. Okay, and there's a little bit of a more subtle one, which is this folding one, and you can imagine this as follows. So you can kind of trap your tube between two walls, and then you can multiply the tube by an interval, and then your tube will hit these walls. Okay, but now you fold these walls down, and then when you fold them down, you will have increased also the index of the handle. Okay, so the stabilization takes this guy and here, so here I stabilize also, but note now that the sphere has grown in dimension, the attaching sphere. Okay, so these are the two stabilization operations. And then you let first n tend to infinity, and then k to infinity, and then you get t infinity, which is the space of stable tubes. Okay.
Sorry, Sylvain, sorry, Danny, I think there's a typo on the top right. There should be to tk plus 1.
Oh, here. Yes.
Well, I can't quite see, but yeah, yes.
Yeah, thank you. Yeah, right. So obviously the two stabilizations are different. One only increases the n, and the other one increases both of them. Thank you. So yeah, so like you can see in the picture that this attaching sphere in the picture on the right has dimension 1 more. Okay, so that's our player, and moreover, this map that I was describing, that gives a vector subspace and tells you how to attach the tube. So E goes to T. So this is a map from BO Kn to T Kn. This stabilizes to a map BO to T infinity, which is called the rigid tube map. Okay, so this is a rational equivalence by a theorem of Bökstedt, and is in fact injective on homotopy groups, and this was essential input for their proof of existence of generating functions. So this is a very important map, and the story goes on. So this map actually fits into this beautiful commutative diagram where the columns are fibration sequences, and it was discovered by Waldhausen. And over here, I just have the J homomorphism. And over here, I have the following thing. So this is the rigid tube map. This is the space of stable H cobordisms of a point. Here, Gn is just homotopy equivalences of Sn. So G is the limit of all of these guys. So in particular, its homotopy groups are just stable stems. And this is the classifying space for spherical fibrations. So the map here just takes an H cobordism and puts it on top of a standard rigid tube. Okay, and the map here takes a tube and just thinks of it in the topological category. And the map here, this is the Hatcher map. It's a beautiful construction of Hatcher, which was proved to be a rational equivalence by Bökstedt. Okay, I would like to talk more about this diagram. There's a lot of beautiful pictures to be drawn if you try to understand this at the level of surf diagrams, but I'm running a little bit short on time. So I will just say that anything that comes from here or here has trivial bordism. Okay, and however, our theorem for existence of generating families on tube bundles doesn't give us any restriction on what tube bundle we have. So instead, we're going to build our theory using this map, and we're going to extract our constraint on the frame bordism class using the map T infinity to BG, which takes a tube bundle and just remembers its underlying spherical fibration. Okay. So now I'm ready to talk about the Waldhausen derivative. And what is the Waldhausen derivative? Well, suppose that you have a tube bundle. So extend n, the outwards normal, to the boundary of the tube to a non-zero vector field on, let's say that all my tubes are standard below height -1. Okay, so what is this? So this is height -1. Okay, so here's my outwards normal. And now I need to extend it to a non-zero vector field. And well, it's kind of clear how to do that. I just need to put the critical point below this line and then fill this in. Okay, and then what you do is restrict to height equal to -1. And so you get a family of maps from Sn to Sn of degree ±1, parametrized by M. And now to do this parametrically, you might say, oh, well, I might run into trouble. And if you do, just stabilize K as much as you need so that you remove all obstructions to doing this. And moreover, you can stabilize once more, and then you have that this extension is homotopically unique. So what you get is from a map from M to T infinity that classifies a tube bundle, you get a map from M to G. And this is the Waldhausen derivative. And in fact, this comes at the level of spaces. And because really the definition that Waldhausen gives is simplicial, this is essentially a construction of this map at the level of spaces. So it's a map like this, okay? And now the obvious but key lemma is that if I have a class here that classifies a tube bundle, then the Waldhausen derivative of alpha, so this induces a map on homotopy groups, the Waldhausen derivative of alpha is just the bordism class of W under the Pontryagin isomorphism. Okay, and this is obvious because you can, what happens, like what is the Waldhausen derivative? It's the restriction of the vector field to this line. But then how do I obtain the frame bordism class? Just by extending it below standard at infinity, and then taking the zero set. But that is precisely Pontryagin Tom on find the stabilization of the alpha. But this is all stable. So it's just Pontryagin Tom on alpha. So that essentially proves the lemma. And now we're pretty good because we have been able to relate the object of interest namely the frame bordism class, to this Waldhausen derivative. And okay, so this is where I have to invoke a result of Waldhausen and well, the order doesn't matter, Waldhausen and Bökstedt. Which is the following, which is that the Waldhausen derivative which is a map from T infinity to G, factors as the forgetful map, which I told you before, the one that to a tube bundle just remembers the underlying spherical fibration, and then the map BG to G, where BG to G is given on pi n in the as follows. So remember that pi n BG, well, pi n G is just the stable homotopy groups of spheres. Pi n BG is pi n minus 1 stable. And what is this map? It's multiplication by eta. Okay, that's n not equal to 2, but that's kind of a trivial case, so forget about it. Okay, and this is actually very geometric. You can extend the derivative on BG by essentially the same definition. And then what's kind of less clear is that the map that you get BG to G admits this description. But okay, so this is what K-theorists tell us. And so at this point, this basically completes the proof of our theorem, because then if I have a Legendrian, which is generated by a function, then for some framing, namely the induced framing, this is just the bordism class of the bundle, which is equal to the Waldhausen derivative of the classifying class, which is a multiple of eta. And then if you want to get the result that I stated for homotopy spheres, you just translate this in the co-kernel of the J homomorphism, and you get the result. And then it's similar for some other homotopy sphere. Okay, so I've run out of time, so I'm definitely not going to talk about higher Whitehead torsion, but I'll just, advertise that once we have this theorem, we can start to try to distinguish nearby Lagrangians by the higher Whitehead torsion of the two bundles that generate them. And so if the nearby Lagrangian conjecture is true, all of this higher Whitehead torsion should vanish for Lagrangians. So I can find examples of Legendrians which have non-zero higher Whitehead torsion. And in work in progress with Kiyoshi, Igusa, we're trying to prove that the higher torsion of nearby Lagrangians is always trivial. And we might succeed, but I really hope that we don't, because if we don't, then there might be a chance of finding a counterexample and distinguishing it with higher Whitehead torsion. So you know, one has to be optimistic in life. It's being enclosed because of coronavirus is terrible, but at least this network of seminars across geographical borders and time zones has appeared, so that's good. And now these are troubled times, but maybe there will be a new step in the civil rights movement towards everyone getting treated equally by the law and its enforcers. So always keep that optimism. Okay, I think I'll finish here. Thank you very much.
Okay, let's thank Danny for his talk. Questions for Dan? There's a comment and question from Hiro. Hiro, feel free to unmute yourself.
Sounds good. Danny, thank you very much for the wonderful talk and the social justice shout out there at the end. So I have a tiny comment and then a question. The tiny comment is you wrote that the map from G to the sphere is an isomorphism on pi n for all n, but of course it's only true for n bigger than or equal to 1.
Sorry, what is an isomorphism?
The map on homotopy groups between automorphisms of spheres and the sphere.
Oh, Yeah, yeah. I mean, I'm only interested in n starting at 7. So
Totally,
so
yeah.
yeah. Okay.
But I have like a classical question, which is about the Waldhausen and Bökstedt factorization.
Yeah.
Could you just give some geometric intuition as to why that should be factored by smashing with the Hopf vibration? Like, I don't understand what this says about families of vector fields.
Yeah, I mean, I'm trying to understand it myself. It might be the following thing might be interesting. So or might help. So first of all, there's a map from BO to O, which is literally, or well, not literally, but it's almost literally taking the derivative of a quadratic form, taking a quadratic form and thinking of it as an invertible matrix, which up to homotopy is the same as an element in O. So this is the derivative. And then you can go to the space of tubes, and then you can take the Waldhausen derivative, and then you can fit this in with the J homomorphism. So in that sense, so then you can maybe ask the question for BO to O, where it's a little bit more explicit, and then you can just do the computation by hand, and see that it's true, that if you start with the generator of pi1 of BO, then which is, you know, this guy, then you'll end up with the generator of pi1 of O when you take the derivative. And so you can at least convince yourself that it's true at that level. To then show that it's true for all n, formally you can just proceed by saying that two spaces are equivalent as threefold loop spaces, but that's not very satisfying geometrically. And I'm convinced that there should be a better geometric way to see it in general, but I'm afraid I can't say it. This is even less geometric, but I can't also resist the temptation to say that not only does this extend, but you can actually even extend this to oops infinity, S infinity, and here A theory of a point, which is just the K theory of the sphere spectrum. And then this is the splitting map, which gives Waldhausen's famous decomposition of A theory as the product of loops infinity, S infinity with Whitehead diff of a point.
Danny, are you writing something? If you're writing something, the screen seems to be frozen.
Damn it. Yeah, every time I stop. Yeah, I got warned about this, but somehow I wasn't able to avoid it. But thank you for letting me know. So yeah, this is what I was writing. That must have been confusing. Yeah, so you have this derivative map from BO to O that's on the left. And that is really the derivative. And so you can check that the square commutes at the level of pi1, and it's pretty convincing. And then you can deduce that the statement in homotopy groups just from the fact that two spaces are equivalent to threefold loop spaces. But that is not very satisfying geometrically, and I am trying to understand it. If and when I do, I will let you know.
And you mentioned something about the existence of these generating functions implying the nullness of the stable Gauss map.
Yeah. So right. So it's a corollary of their work that in particular the Gauss map is null homotopic when L is a Lagrangian homotopy sphere. In general, they only know that the stable Gauss map is 0 on homotopy groups. So we actually don't, it's an open question whether the Gauss map is always trivial, but for spheres, you do get that it's null homotopic. It's a little bit disingenuous to call it a corollary of the result, because that's kind of, in some sense, the central point of their work. But yes, they prove that for sure.
And is there any way you can see the Hopf vibration here as an element of like U mod O? Yeah, I'm just trying to understand the relationship between the factorization theorem of Waldhausen and Bökstedt and the existence of generating functions.
Yeah, I mean, in my mind, they are separate phenomena. Like the factorization gives you a statement about the bordism class of any Legendrian that admits a generating function. Mm-hmm. So that applies, yeah, to a vast number of Legendrians. And then it is a remarkable fact that nearby Lagrangians in cotangent bundles of sphere admit generating families. But that, I think, that follows essentially from the Guillermou doubling trick and from Bökstedt's theorem that the Hatcher-Waldhausen map is a rational equivalence. So I don't see how the Hopf vibration comes up in there, but maybe Mohammed can comment if he has anything to say.
Since I'm explicitly named, I'll say, I think the Hopf vibration is some kind of red herring. I think there, in the sense that if you really had more structure that you were keeping, you would realize that it's not the Hopf vibration that's going on here, and it's just that you have some map that is intrinsically and geometrically defined that, for example, gives rise to the map from BO to O, and that map happens to be homotopic to the Hopf vibration. And the best discussion I know is in the paper of Bökstedt, where he describes this map from BO to O as a map from S1 cross BO to BO that is completely geometric, and it has to do with taking like two copies of a vector bundle and twisting them via the map, which swaps the two-factor, and then gluing them together as a bundle over the circle. And then he computes that gives rise to the Hopf map. So I think looking for the Hopf map itself in the geometry of T infinity and pseudo-isotopy is probably not the right thing. It's really this geometry that, again, Bökstedt noticed, and then there's a computation. So that's at least my point of view on this.
Yeah,
Okay.
I would agree with that.
Thank you.
Other questions, Danny?
Sorry, I'm going to barge in. Sorry, Danny. I think at the very end of your talk, you said, something about SN and also the same about exotic spheres. And I feel like when you were giving the talk, you didn't actually highlight at the beginning when you were stating the results, you did not highlight this point, although maybe I missed it, which is that unlike all previous work, which really only gave a result for the standard sphere, okay, and maybe put in extremely strong assumptions to say something about Lagrangians in cotangent bundles of exotic spheres. This work really makes some kind of uniform statement about all cotangent bundles of exotic spheres. Because all you have to do basically is kind of shift by the appropriate coset. Like take the difference and then you make a conclusion about it. And it wasn't clear to me that you actually said it like this.
Yeah, it's supposed to be the statement of that.
Oh, you actually said it. I'm sorry. I apologize.
No.
You said it. The statement of the theorem that is currently written right now is exactly the. So maybe then I just want to remind people that the statement here doesn't require sigma 0 to be a standard sphere, unlike the previous work that we had that used whatever I and other people did using holomorphic curves. So this is kind of some indication that this is kind of a much more scientific approach than the kind of craft artisan stuff that we did.
But I think that this Ekholm and Smith work also does not require this, does not have this assumption, right?
Ivan is online. He can say something if he still is online.
Yeah, I mean, I don't know if he's online, but my understanding is also that they proved it at least, if not always, sometimes for more general homotopy spheres. Let's see.
There's a question from Yue. You're welcome to unmute yourself.
I mean, if I can paraphrase my question properly, that does your theorem somehow relate to the fact that topological Foucault category admits a Waldhausen S dot construction?
I have no idea how to interpret this in terms of the Foucault category. Yeah, I have nothing to say.
Can I ask a kind of a question following up on Mohammed's comment? So in the previous work, there was some important role was played by like some standard Lagrangian embedding of the sphere, like for example, a Lagrangian sphere in like CPN cross CN plus 1 or so. Right. So first of all, can you sort of,
no.
Is that just completely gone from this result? And does somehow that embedding feels like it's related a bit to the Hopf vibration? Is there any way that's somehow connected to the hop map showing up here? Or?
I do not see how. I mean, like Mohammed was saying, this is really kind of a very structured approach that at least the way that you get twisted generating functions is extremely systematic and works the same over any manifold. Really, the theorem that they prove is that there's always a twisted generating function. And then a miracle happens, and for Sn, you actually get an honest generating function. But I have no way, I do not know how to see this from the viewpoint that you say of that very specific Lagrangian embedding. But again, Mohammed, if you have something to say, please go ahead.
No, I don't know how to relate to the generating function approach to basically the constructions that we had in other dimensions in using homomorphic curves. One thing I can say is, Danny indicated this, which is that he's basically underselling the result. I'll say it again, in the sense that it's clear that this method will give a result for other manifolds with more complicated topology. Right. It's just that you have to the classification. In fact, I can kind of say right now what I expect the result to be. There is this theorem that he mentioned, which is actually currently on the board, which is about this Hn. And you should think of this Coker J as, roughly speaking, the image. So in the surgery classification, there is the structure group and the set of normal invariants. And the set of normal invariants is maps to G mod O. And the set of normal invariants, you can ask for things to be in the image of eta. And that's the statement that I believe one can eventually prove using these methods. That for every manifold, if you look at some exact Lagrangian in its cotangent bundle, you think of that as an element of the structure group. As an element of the structure group, it maps to the set of normal invariants, and its image under the set of normal invariants is also in the image of eta. Okay, so you have to formulate that, but that is a statement, and then you can go from that and just compute. For spheres, I believe it exactly recovers all these computations once you compare Kerver-Milner to classical surgery theory, and for other manifolds, it will give other results.
Yep.
There's a question from Hiro. Hiro, go ahead.
I apologize if I just missed this part. My connection was in and out, but your title had K-theory in it, which I assume has to do with A-theory.
Yep.
Did you already mention the connection?
Oh, well, I did it at the very end. So the connection is well, okay. So our key player is the space of tubes. Okay. And this fits into a homotopy Cartesian square where this is BG, this is A theory. Now, the Waldhausen derivative, like I say, factors through BG. And in fact, you can make this diagram commute like this, where this is the splitting map. So this map splits the previous map and then gives this decomposition like this. So the splitting, so I guess the point is the Waldhausen derivative is the splitting map in disguise, just in the space of tubes. And so we are, I mean, we're not actually using anything that deep about A theory, I don't think, but the story is clearly in that ballpark. And it is possible that some deeper results about A theory might have some further role to play in this story.
Okay, thank you.
Yeah, I mean, I will just say, some stupid invariant that you can give of well, I don't know if it's stupid, maybe it's not, but some stupid invariants that you can give is just what are the homotopy classes of maps such that lambda admits a generating function on this tube on this guy. So for instance, for n equals Sn, this is a subset of the homotopy groups of T infinity. And so at this point, you're defining a Legendrian invariant in terms of the homotopy groups of T infinity, which by this homotopy Cartesian square are intimately related to the homotopy groups of the algebraic K theory of spheres. And okay, so these homotopy groups have a lot of torsion, but they do have some rational part. And so this higher Whitehead torsion that me and Kiyoshi are thinking about can study the rational part. But additionally, of course, there's a lot of torsion information there that could potentially obstruct the Hamiltonian isotopy class of a nearby Lagrangian.
Okay, well, I think this would be a good time to thank Danny again.